Good afternoon. We're here to talk about the Slurm Bridge, part of the Slinky project, bringing Slurm scheduling superpowers into the Kubernetes stack. I'm Tim Wickberg. I'm the CTO for SchedMD, the main Slurm developers, and
Alan good mic check. I'm Alan Mutschelknaus, one of the developers on the Slinky team.
So, to start with, what is Slurm? Slurm is a leading HPC workload manager. The term workload manager roughly means it is both a job scheduler as well as a resource manager, allocating resources out on individual compute nodes, providing orchestration and management of individual compute processes out on those. This all roughly equates in the cloud-native ecosystem into an orchestrator such as Kubernetes. The scheduling part, again, is kind of this higher level process that is prioritizing, deciding what compute jobs, what simulation jobs to run on what section of the system. Resource management layer is really dedicated to the lower level plumbing of getting processes bootstrapped and executing on actual compute nodes. Slurm itself was originally just a resource manager. That was the R and the M out of Slurm, but then evolved all of these scheduling capabilities. And some of what we're sort of experimenting with the Slurm Bridge is getting Slurm to behave just as a pure scheduler and actually being able to switch in Kubernetes or Slurm's own resource management layers to do the actual process management and process launch. Slurm manages the majority of the top 500 supercomputers in the world. This is a list that the HPC space has been maintaining for years. We kind of look at that as our benchmark of our ability to get Slurm out into that audience. There is not really an equivalent list to point at for AI/ML workloads, although our market research implies that we do run the vast majority of AI training workloads today because of Slurm's unique multi-node job scheduling capabilities that don't really exist directly in the Kube ecosystem yet. Slurm also very frequently scales beyond 15,000 nodes in a cluster. We again run on these largest systems on the world. Slurm is open source under the GPL v2 or later license with an OpenSSL license exception, a little distinct from stuff that's more native to the cloud ecosystem. SchedMD, just to step back yet again, we're the developers of Slurm and now Slinky. We actually spun off from Lawrence Livermore National Lab back in 2012 to support and promote Slurm's adoption through more than just the DOE National Lab systems. Our two founders, Mo and Danny, are the MD and SchedMD. We are not medical doctors. Please do not consult us for medical advice, even though our business license says we are allowed to, which is a very weird quirk of Utah making a few clerical mistakes there. SchedMD does commercial support for Slurm and now Slinky alongside training, consult, and custom development. That's our revenue stream to support all of this work we do. Everything SchedMD builds is open source. Support revenue is what lets us go and build more of this and support it broadly. So what is Slinky? This is our very simple little equation. Take Slurm and Kubernetes. Slinky sits at the intersection of these two stacks. It is what lets us coordinate between the two sides. So Slinky itself, we try to describe it as a toolkit of related components to integrate Slurm into Kubernetes. Those different components are designed to be able to mix and match with one another, but they can also be used standalone. We've had the Slurm operator out for a number of years as sort of the first major component we published. Slurm Bridge is sort of the newer, bigger piece, bringing Slurm directly into the Kubernetes scheduling layer. We're trying to build everything here under the Apache 2 license to make it a little friendlier to interact with the rest of the cloud-native ecosystem, not just be solely isolated to more of a GPL space that is not always as friendly with some of the cloud environments. So why tackle both? What we're seeing and what's driving a lot of the work we do here is this idea of traditional cloud-native systems having a lot more batch-type computing work to process. There are a lot of different tricks and prioritization mechanisms and other things that we think can come over from the traditional HPC batch computing ecosystem and better inform how to run these same classes of workloads in the cloud-native space. We also are seeing a lot more demand for sort of hybrid and converged environments where you have batch computing demands adjacent to maybe production operations, trying to figure out how to service both out of one unified set of compute hardware rather than needing to build separate silos for, say, your training regime versus your inference side. And Slinky is meant to be our intersection of this and the way that we promote this converged model of computing between the two halves. And in terms of additional capabilities and kind of what we think Slurm can bring to bear in this environment is a lot of different things that the HPC scheduling community have been expecting, developing, and putting a lot of thought into over the last several decades. One of the major things that we're seeing and what drives Slurm's preeminence in the AI training space is that multi-node scheduling is a default capability of HPC batch systems. That is a baked-in assumption. It's not something that's being retrofitted on top. That then shows up in support for advanced topological computing, especially being able to optimize like network layout and network placement for interconnects like NVIDIA's DGX systems, making sure that the planning for those simulations matches the underlying interconnect and are efficiently placed for best performance. Then this other related concept that's a natural extension of the idea of multi-node workloads being a first-class citizen is this idea of backfill scheduling, of needing to plan not just the instantaneous use of the cluster, but plan the cluster's use through a broader time frame. When you can't instantaneously run everything you want to on that same compute hardware, how do you prioritize and manage everything going into the future? And with that, I'll turn it over to Alan to talk about the Slurm Bridge.
Okay, thank you. Yeah, so I'm Alan. I'm going to walk through what Slurm Bridge is and how we're managing to schedule Kubernetes pods using Slurm. So this first technical diagram is kind of a mental model that exists in my head. That we've got this multiverse of schedulers right now with Kubernetes and Slurm. And so how can we kind of merge them together, getting the best capabilities of both? And that's where Slurm Bridge comes in. So Slurm Bridge is a it's using Slurm as a Kubernetes scheduler, and we're using the Kubernetes Scheduling Framework. So Kubernetes Scheduling Framework, a couple of the extension points that we're using for node placement would be pre-enqueue, pre-filter, filter, and post-filter. That's kind of the extension points where we decide which nodes a pod should run on and when those pods should run. We're also using a pre-bind hook to generate DRA resource claims if we see that a pod needs to have that generated for it. So that's kind of the Kubernetes feature that we use. We're using the scheduling framework. But how does Slurm itself know about these pods? And that's where we come up with the step where we translate the pod resources into what we call a Slurm placeholder job. So I kind of view that as like the outline of one or more pods into this Slurm placeholder job. Internally to Slurm, that's also kind of referred to as an external job. And that's a construct that Slurm has to say, here's a job. Go ahead and make a placement decision for this job. But when it comes time to actually launch the job, understand that something else is going to do that on your behalf. And in the case of Slurm Bridge, that would be kubelet. This idea of a placeholder job is similar to what's coming out in a subsequent release of Kubernetes, I think 136, where there will be a workload resource type. And that's kind of this abstraction around multiple pods. How do we represent a piece of work might not just be one pod, but it might be multiple pods. So we're looking forward to that workload resource type. I think that will help us in how we derive our placeholder job. But for now, we're kind of having to do our own homework and figure out which pods sort of belong together. So to summarize, Slurm Bridge, we're scheduling pods by Slurm, but they're launched by kubelet. Slurm obviously needs to know what types of nodes are in the system, so you have a couple different options for what Slurm nodes you have. The first kind of variety we sort of call like a hybrid type deployment of a Slurm node, where you might have both slurmd and kubelet on the node. And in that way, you could still leverage slurmd to run your traditional Slurm batch workloads with Slurm client commands, like srun and sbatch and salloc. Or you could have kubelet be fielding those placeholder jobs and running the pods from Slurm Bridge scheduled pods. Or just like we have this external job, we have the concept of an external node. So because kubelet's doing the work of launching the pod, we can also kind of take that one step further and say we don't really need slurmd running on the nodes. We could just have kubelet running there, provided we tell Slurm, there's some nodes out there. This is what resources it has, CPU and memory, but just, there's kubelet out there running instead of SlurmD. This is the scheduling framework that I mentioned before. I'm not sure how many people are familiar with this, but this is how the main Kubernetes scheduler processes pods. Kind of to go over this a little quickly, pre-NQ, you've got this first opportunity to kind of inspect pods before they get to the main scheduling loop. Those pods are then sorted, and then you evaluate them one at a time. And these filter phases are where you're kind of reducing the set of nodes that could run this pod. So you kind of filter down from all the pods, nodes. You filter down from nodes in the system to say which nodes could this pod run on. And then when it gets time to score it, you're scoring what's the best node for this pod to run on. And then you move on to these reserve and permit hooks before it's time to run, and you hand it off to this binding cycle, which is this asynchronous process where you finally let kubelet run the pod. So this is Kubernetes, like the main way that you schedule pods, and these different extension points where you can modify this behavior. But if we kind of recontextualize this in Slurm Bridge's perspective, I'm going to kind of re-illustrate this diagram showing where along this path that we're operating on the pods as a scheduler. So we get to this pre-NQ phase. We're just making sure that a pod has a toleration. It's important for us to kind of fence off some nodes that Slurm Bridge is scheduling for. And we do that with this no-sched taint so that pods don't, like the main Kubernetes scheduler wouldn't land pods on these nodes that we're trying to schedule pods on. So that's pre-NQ. Then we're moving on to this pre-filter phase. And this is kind of the first point in time that the Slurm Bridge scheduler would look at the pod and say, does this pod have a placeholder job associated with it? And for the purposes of this talk, let's just say it is the first time we've seen it, so we'll ask the question, and the answer is no, it doesn't have a placeholder job. We haven't seen this pod before. So now we're moving on to this filter phase where we're trying to figure out which nodes could the pod run on. What we do here is we let some of the traditional filter plugins run, like taints and tolerations, or the volume claim plugin. And this is a way for us to kind of figure out if Kubernetes were to have picked some nodes for this pod, which nodes would be valid for it. And that's important because Slurm doesn't necessarily have the primitive of a taint or a toleration, and that's not something we can directly map into Slurm. But by letting Kubernetes kind of do this pre-processing to figure out which nodes would be valid nodes for Kubernetes, we can kind of derive this list of nodes that we can base our placeholder job on. And then we just make sure that one of our filter plugin is the last one to evaluate, and we can kind of make the assumption that if we get to our filter plugin, we know it actually would have been an okay one for Kubernetes. And our filter plugin is kind of just a simple check. Does it have this special annotation that says Slurm Bridge gave this pod a node? So again, because it's the first time, none of that has happened yet. So we say, no, it failed the filter check. But we get to now post-filter. And traditionally, post-filter, you might be doing some preemption, where you're clearing some space off the system. If your pod has a higher priority, you can kind of eject some lower priority pods and make space for your pod. But that's not what's happening with Slurm Bridge. What we do is we use that input from the filter phase, what nodes are acceptable to Kubernetes, and then we create this placeholder job in Slurm. So we've now created a placeholder job. Slurm is able to then schedule that pod using its main scheduling algorithm, and then we kind of get back through this feedback loop to pre-filter. It can ask the question again, and maybe there is a placeholder job, but maybe it's not running yet because Slurm has a full backlog of work and it's not getting to this placeholder job yet. So the answer could still be no, and that you have to kind of reevaluate this loop over time. But to get things progressing, let's say that yes, the placeholder job does finally run. So we kind of do this work where we hand out some nodes to the pods associated with that placeholder job. And from pre-filter, we can just return the single node that we're approving from this pod. And then at that point, the filter check becomes this kind of rubber stamp where we say, yes, Slurm Bridge approved this node for the pod. And then we can proceed to the binding phase where we actually let the pod run. So that's how we're using the scheduling framework to kind of create these placeholder jobs. So that Slurm can understand how to schedule it. This diagram shows what's running on a system when you're using Slurm Bridge. To highlight here, we've got like an admission controller just to check that pods have some sane defaults, or it has that toleration for the taint that I had discussed. The Slurm Bridge scheduler itself running as a pod, as well as a controller. No Kubernetes component, I think, would be complete without a controller to do some reconciliation. But this is really important because we have pods that we've now replicated in Slurm as a placeholder job. So there must be some entity in the middle kind of reconciling both of those worlds. You could imagine, like, if your Slurm placeholder job had some sort of time limit associated with it, and that no job should exceed a certain time boundary, and your placeholder job gets terminated by Slurm, it's up to the controller to go look on the other side in Kubernetes and say, that placeholder job you were associated with is terminated, and so you need to now terminate as well. Or vice versa. Maybe all your Kubernetes pods complete, they finish their work. It's equally important to tell Slurm that placeholder job is no longer needed. We've completed the work, so we can free up resources, and Slurm can kind of chip away at that backlog of maybe other placeholder jobs that are pending. Within Kubernetes, there's also in this diagram, a little mini Slurm cluster where we have the REST API and a controller. So Slurm REST-D is kind of fielding the API requests, and then the controller, Slurm CTLD, this is kind of the brains of Slurm. This is what's actually doing the scheduling, making the decision on where to run those placeholder jobs. And then I've just represented the two kind of flavors of nodes that we've talked about. You can kind of have this hybrid approach with both slurmd and kubelet running. And depending on what type of work that node is meant to use, you could have slurmd actually running regular Slurm work, or you could have kubelet fielding pods that are placed there by Slurm Bridge. And again, there's also a Slurm external node type where you don't need slurmd, you just let kubelet run on there, and we just tell Slurm, hey, there's this external node over there, and you can place work there. I think I've kind of gone through this controller, but again, the controller in the middle reconciling pod events, or pod updates. We watch the pod resource type, and if we have a placeholder job associated with it, we kind of act on it. So if all those pods completed, turn over to Slurm and say, hey, Slurm, that placeholder job should be gone now. Or if there are updates to the Slurm client cache, we can generate events and then reconcile on the other side to Kubernetes to make sure that we're keeping both of these realms in sync. We also do have some cleanup work here with DRA resource claims. If your pod has generated a resource claim, or Slurm Bridge has generated that, we do clean that up because we know that the Slurm Bridge placeholder jobs are representative of those resources, and we'll recreate them if needed. So to summarize, with this kind of design in place using the scheduling framework and placeholder jobs, Slurm Bridge gives you a workload-aware multi-node scheduler. So those pods that come in, we can kind of derive what resource type they came from. Is it a pod or a job set, or pod group or leader worker set? In the case of pod group or leader worker set, it makes sense that multiple pods could be the same placeholder job. So like leader worker set has a concept of a group where in order for that group to be successful, all the pods need to be running, or you should just not run all of them. You should wait until all of them could run. So multiple pods could map to a single placeholder job, and that's how we kind of get Slurm to be able to talk to Kubernetes and do this multi-pod, multi-node placement. And if you configure your Slurm cluster with a topology file, the topology definition of your system, Slurm is just going to intuitively make a topology decision on how to place your pods. So we have topology-aware scheduling. And we do have this DRA support. So when we are kind of doing this translation, we say like either just a regular device plugin, or we're kind of keying off of this DRA capability, the extended resource feature, where you have this little prefix. And we can kind of find out that that would map to a DRA device class. So let's translate that into something that Slurm understands, which is a GRES resource type. So we model it as GRES in Slurm, and then if needed, we can generate a DRA resource claim. Here's a look at the translation, kind of an example translation between a pod and a Slurm placeholder job. So you can see there's some annotations over here that we support. This is just honestly, a pretty simple example of just overriding the job name in Slurm. So you can see in Slurm the job name has been overwritten. Maybe a more interesting thing to do would be to apply your time limit here. If you want to make sure your pod doesn't exceed a time limit, or maybe it's automatically applied, that placeholder jobs only are allowed to run for a certain amount of time, that annotation could be used there. We're then translating the resources into the placeholder job. So how much resources does this pod request? And then here was that DRA style syntax of an extended resource claim, where we can key off of that and find out what device class type it was, and then translate that into Slurm's GRES annotation and a quantity. So when Slurm makes this placeholder job, it's also accounting for, like, say, the GPU requested by the pods. So kind of a static snapshot view of a system. What does this look like when it's up and running? In this example, I've got 3 pods here. A job pod is running, and then 2 these sleep DRA pods. These were actually generated from a pod group resource type, or rather associated with the pod group resource type. We can see that some resource claims were generated for those pods because they requested GPUs. And then if we look at this kind of third block here, that's Slurm's representation of the placeholder job. It's the Slurm queue. It's showing the running placeholder jobs. So you can kind of see job ID 8 here lines up with that job pod. And then we just have a single other job, job ID 9, and that's the pod group pod. So that single placeholder job is representative of the 2 sleep pods. You can see that Slurm picked these nodes 6 and 7 for these 2 pods. And so that's where the sleep pods are running. And then this final block showing Slurm's node level view of the system, which nodes are allocated and which nodes are idle. So we have 2 idle nodes. What would happen if a new set of pods burst onto the scene and they wanted 3 nodes, and they can't get 3 nodes? Well, we can say, imagine that a leader worker set scaled up to do some AI inferencing demand in response to some demand. And so these VLLM pods come up, but they're pending. And the reason they're pending is that this placeholder job in Slurm is pending, waiting on 3 nodes. So Slurm says, I'm waiting on more resources to be available, so these pods remain pending. And you can kind of see, yep, there's only 2 idle nodes, so those pods would just stay pending until the Slurm decides that it's time for the placeholder job to run. So if we've kind of let the first 3 pods complete their work, those go complete, the placeholder job, job ID 10 in Slurm, starts running. And then we can see that's got these kind worker nodes, kind workers 5, 6, and 7, and those line up to the same pods or same nodes that are assigned to these pods. Okay, that was kind of this static view, but I can kind of show a system up and running. This is running locally on my machine. We have a little script in our repo, this kind.sh with --DRA example. That's installing an example DRA driver. So you get some nodes with some fake GPUs to play with. Got some leftover things over here. Let me just delete that real quick. We can show with this setup, you get a few kind nodes, and then we've got within Slurm, 5 of these nodes are registered as in the Slurm partition. So those are the nodes that Slurm's going to use to schedule against. If we look at the pods that are running, here are some of the pods that we've talked about. So Slurm Bridge, we've got the admission, the controller, and the scheduler. And then I'm using another Slinky component, Slurm operator, to stand up my own little mini Slurm environment in this cluster. And if we look in the Slurm namespace, this would be like the bare minimum pods that you would need from Slurm to do Slurm Bridge. Normally you might see like Slurm accounting or a Slurm database. But here I just have the controller and the REST API. And I'm just using external nodes, so there's no Slurmd running. So just controller and REST API in this environment. Let me just apply one of these resources. So I'm going to apply a job that creates 1 pod, and it does make a DRA resource request. So we get a DRA resource claim generated here. If we wanted to, so this is doing scontrol show job on the placeholder job, which is job ID 38. So here we can see kind of a blown up view of the placeholder job. Kind of some things to point out here is like this requested node list that was generated from that filter kind of feedback loop that I highlighted earlier, where those nodes are valid nodes that Kubernetes could have used or would be valid for that pod. So we hand those kind of, feed that information into Slurm. And we can see also we leave a little bit of a breadcrumb here in this admin comment to know from Slurm's point of view which pods is this associated with. We can do like this pod group example, our two sleep pods here with a single placeholder job. That one, I would guess, would be 39. So here's the multi-node, multi-pod example. Now we have two pods associated with a single placeholder job. And if I were to, say, scale up this, let's say the leader worker set needed to scale up, we could scale that up. Now we've got these three pods that came onto the scene. And in this case, there were enough nodes available, so they could immediately start running with this placeholder job. Okay, this is the demo I had. I guess we can open it up if folks have questions or interested to hear more.
Hi, thanks for your talk. I'm curious to know, I think is it the Flux operator that's out of LLNL? I don't know, there's a bunch of projects in this space that are all kind of trying to do the same thing. So I'm curious if you can just say a few words as to how Slurm Bridge compares to those.
Okay, I'll just hand the mic back and forth. No, there's quite a few different projects, all have slightly different spins on it. Flux, Flux, specifically the scheduler Flux, not FluxCD, not the other half a dozen Flux, is interesting. It actually has a bit of shared lineage with Slurm, but they have a slightly different take on a lot of stuff here. We're not directly trying to compare what we're doing with Bridge to their approach. It is a little different, and sort of we're assuming and positioning Slurm to be the top-level scheduler across the whole converged set of infrastructure, which is a little different.
So instead of, I mean, it looks pretty complex, especially like trying to sync context between two different worlds, trying to do or achieve similar stuff. Is there a better way to achieve the same thing without having so much complexity, where like you run something like a placeholder pod on each node and then from there manage all resources, where Slurm takes over and then Kubernetes is just a means of deploying stuff and Slurm is a means of doing the actual job and scheduling and managing resources?
I mean, I think ultimately we do need a way to represent the pod in Slurm. That's kind of foundational to how we do that scheduling. So we do need to kind of model it in Slurm, and that kind of introduces that need for the reconciliation between the pods and the placeholder job. So I think that is kind of core to what Bridge is doing.
I guess to expand on that, the part that from my level is sort of the most nuanced is the work that we've had to do to translate all of the different representations of multi-node work that are kicking around in the Kubernetes ecosystem. Job set, pod group, leader worker set, trying to map those into Slurm's canonical representation of multi-node work is where a lot of the complexity of what we've had to implement in Bridge comes from. We've been working with a lot of the scheduler groups. There was a full day of discussion kind of around a lot of this about what would it mean to go introduce really a true multi-node primitive into the Kube ecosystem. Something like that would actually help reduce a lot of the complexity of what we're doing in Bridge. The actual reconciliation loop is really not that difficult. It's just our way of communicating back and forth. Slurm doesn't natively have a bunch of asynchronous hooks where we can just dial directly back and forth. That's something we may pursue, which would move us away from this reconciliation model to something that's a little more event-driven. But that's a little further down the road. This was just sort of the easiest path to pursue for now.
I see. Okay, cool. Thank you.
And that I'm getting told we're out of time. Thank you all. Alan and I will be sort of floating around in the lobby. We do have stickers here if anyone wants to grab them. We don't have a booth this year. We might in future, but that's our whole swag pile is up here at the moment if anyone's interested, or feel free to tag us and say hi later. Thank you, guys.